My name is Erika Reith, and today I'm going to be talking to you about the Nature Brevia article, "A single amino acid residue can determine the sensitivity of circas to artemisinins." And for a little background, a circa, for the purpose of this presentation, is a sarcoendoplasmic reticulum calcium ATPase. I'll get into that in a little bit. So, the most important thing that you should know about artemisins is that they're the most important and most widely used anti-malarial drugs. They're commonly used to treat several complicated types of malaria, such as Plasmodium falciparum and Plasmodium vivax. For the purposes of this presentation, they mostly discuss it in the context of Plasmodium falciparum. And one of the most important things about this type of malaria is that it needs to be combated aggressively in the beginning, but these artemisins are usually combined with longer acting drugs in order to combat the complicated resistance such that they might come back months later. Also, the inhibition of the Plasmodium falciparum ortholog, the PF-ATP6, in P. falciparum is basically the way that these drugs work. And what's interesting is that there's a peroxide bridge located in the middle there where the arrow is, and the peroxide bridge is unique, and it's thought that this is the reason that these drugs work, by creating free radicals that eventually cause the parasite to die. So the experimental setup of the way that they did this study is that they took wild type and mutants, and they initiated the binding of the artemisinins to these circa orthologs. And these mutants can involve mutations of amino acid residues. And the way that they studied this binding was with an ATPase assay, because the ATPase is what a circa is, and so the ATP hydrolysis is the way that they kind of quantify whether this artemisinin drug is binding. Finally, they want to test the sensitivity of these mutants in order to understand whether amino acid changes can affect the way that these artemisins bind. The way that they quantify sensitivity, which I'll talk about later, is with the Ki values. So leucine 263 is an amino acid that clearly modulates artemisinin sensitivity. So here they kind of just show energy minimized structures of the circa orthologs, this one being the most important. Here you can see an artemisinin is bound, and these different M3, M5, and M7 regions are the helical binding regions of interest. And if you'll notice, leucine 263 is right there, and that is one amino acid that they characterize to be essential to the binding of these artemisinins. Here they sequence these different M3, M5, and M7 regions. So this M3, where the leucine 263 is located, is shown here. And of particular interest is this magenta region, which is the leucine 263 region. And they found that when they altered amino acids around this leucine 263, they got vast differences in the artemisinin sensitivity to these circas. So the only thing that I want you to understand about this table is the Ki values. And if you can look and see, this leucine 263 wild type has about 169 value for the Ki. And you can notice that these different orthologs and these different mutations create vastly different Ki values, changing the way that that artemisinin can inhibit this ATPase. So to summarize, a single amino acid mutation in these circa orthologs can produce vastly different sensitivities to the anti-malarial class of artemisinin drugs. And through this paper, they've understood that newly acquired structural and functional insights into these circa structures can better guide future directions for the design of artemisinin drugs. So, to summarize once more, beneficial amino acid mutations, whether that be changing a leucine to a different amino acid or perhaps in some cases adding an extra leucine, can increase artemisinin sensitivity, and decreased resistance can be acquired for this most widely used antimalarial therapy. Thank you.